Hi, in this video we present the work Simple and Low-Cost PLC Modem for IoT Applications. Internet of Things is an emerging concept that's drawn attention from both academics and industries. One important part of the IoT device is its communication modules that are responsible for connecting the IoT device with the cloud and also with the other device. Wireless communication, such as Wi-Fi, Bluetooth and LoRa, are usually employed in IoT due to its easy installation. However, this technology suffers from attenuation by obstacles, often requiring the use of repeaters, which can make the wireless network relatively complex, expensive, and difficult to install and maintain. One alternative to the wireless technologies in IoT is the power line communications, in which the existing electrical wiring infrastructure is used to transfer digital signal between devices attached to the power line. PLC is not subject to interference due to obstacles, such as walls and furniture, and due other communication links, which makes this technology in many cases the best solution for IoT applications. Recent works in PLC focus mainly in increasing the transmission data rate. They are especially useful for devices that require fast communications, such as computers, TVs, and cameras. However, many IoT devices, such as smart meters, smart lights, air conditioning, and presence sensors, do not require high data rate communication. In this context, we propose in this work a novel, low-cost, narrowband PLC modem for low data rate applications. The proposed PLC modem is very simple. It's composed basically by OOK modulators and demodulators, followed by very simple bandpass filters. The receiver also have an controllable amplifier that can select automatically the gain in the received signal, and it couples with the power line through ground and neutral wires, which makes the system even simpler since it does not require complex isolation circuitry. The modem connects to the microcontroller that is part of the IoT device through UART communication. This picture shows up the circuitry of the transmitter. That's very simple, composed by only discrete components: 3 transistors, 5 resistors, 4 capacitors, and 1 inductor. The receiver circuitry is also very simple, composed only by 3 transistors, 14 resistors, 8 capacitors, 1 inductor, and 1 analog switch. This circuitry has the capability of adjust automatically the gain of the receiver, and it allows for the application of the system in place with different noise levels and attenuation. We present in these photos the final version of the proposed modem. This PCB also includes a microcontroller and its auxiliary circuitry that can be used to implement the IoT device. The first tests were executed in a controlled environment, with the modems disconnected from the power line. The power line was emulated by a pair of wires, and an arbitrary signal generator was used to inject active white Gaussian noise in the channel. An oscilloscope was used to observe the signal and measure the spectral noise. We connect in the channel 2 PLC modems, one operating as a transmitter and other as a receiver. The transmitter was configured to send a package of 5,000 bytes with the content in binary of interleaved zeros and ones, resulting in 40,000 bits with a baud rate of 9,600 bits per second. The carrier frequency was fixed in 500 kHz, and the adjustable receiver gain algorithm was executed before running the tests in each noise spectral density. The results of the bench experiments are presented in this table. The adjustable receiver gain algorithm worked as expected, decreasing the gain when the noise is high and increasing the gain when the noise is low. The system presented no errors when the noise spectral density is below 111 nanovolts square per hertz. And it also shows that the system is capable to work in very noisy environments, with errors below 5% when the noise is below 444 nanovolts square per hertz. The developed modem was also tested in a residential installation of typical appliance connected to the power line, where it showed to have errors below 1.2% in all situations. In this work, we presented a simple and low-cost power line communication modem for low data rate IoT applications. Low cost was achieved by using neutral and ground conductors as communication channel and implementing a simple on-off keying modulation and demodulation in hardware. The modem shows capable to transmit data at 9,600 bits per second and has no errors when the noise spectral density in the power line is below 111 nanovolts square per hertz in the bandwidth of 500 kHz. In a typical house environment, the mode presented error below 1.2%. The algorithm proposed to adjust the gain of the receiver, amplifier, and the carrier frequency improves the robustness of the system, and the proposed modem shows considerably simpler than the others presented in the literature, being very suitable for low-cost applications. Thank you.